So they can be called reaction pathway diagrams, they can be called reaction energy diagrams, or reaction energy graph. Doesn't really matter which one. The biggest thing today is that we're learning how to read them and what they tell us. So this graph represents as a reaction proceeds, so the x-axis is as the reaction is going, the energy changes that are going on, and that's what the y-axis represents, is the numerical value of the energy we've measured that's happening. Okay? So a few key parts of the graph we need to start off with in knowing, as we're looking at the change in energy, is so when a reaction begins, before anything happens, we just have our reactants. So write this in on your picture. Okay, that this first line right here always represents the reactants, the potential energy that they have. In order for our reactants to become products, they have to get over the hill. They have to get a certain amount of energy, otherwise we stare at the reaction and nothing happens. Okay? The trick is I often imagine it like a mini golf course. So you know, like on a mini golf course when there's a hill, right, and the little holes on the other side. If you don't hit the ball hard enough, this happens to me all the time, what happens? Yeah, the ball rolls up, but it comes back down, right? Same thing, if I don't give it enough energy, no reaction will occur. But then once your ball gets to the top of the hill, then the reaction will just proceed. Okay? So the end goal right here, this represents the products.
Does it ever stop and then pop?
So tell me this, in mini golf, what's the probability of the ball stopping at the top?
Not very high.
Not very high, right? And it's the same thing here. So the peak of our hill is where we get what is known as the activated complex. And it's a very, very unstable spot. It's really not something you see. It's not something you can isolate because once you get up, the energy just continues forward. There are some reactions where if you were really, really careful, you could maybe isolate this. But it's hard to do because normally it just goes so fast. But good question. Okay, let's talk about what these other numbers on our graph mean. So we have our reactants, activated complex, and the products. Okay, so the first thing we want to be able to do is simply looking at a graph, tell me the potential energy of the reactants, the products, and the activated complex. So can somebody by raise of hand have an idea of what the energy of my reactants is? What do you think, Kieran?
So on the y-axis over here it says reactants is 100.
Good. So all we do is we know this is reactants. We line it up with the y-axis, and it's about at 100. And the unit that we're using for this graph is the unit of joules, which is represented by a capital J. If you've never worked with joules before, they're just a unit of energy. Sounds weird. It's not a common unit you're used to if you haven't learned about energy yet, but we'll use it quite often in chemistry. You can often relate it to like a calorie. So that's the energy we use when we eat, right? Calorie is another unit of energy that we can measure in, but in chemistry it's typically the joule or the kilojoule. Good. Okay, oh, Kieran, you have a smiley face. I'll pass those out in just a second. If I give you one and you don't have your paper, just make a note somewhere. Somebody else by raise a hand want to tell us what they think the energy of our products is? Jeff?
63.
Good. And in this case, right, since the graph is not perfect, if these numbers weren't here, and you looked at this and you said like 160, that's fine, right? If it was just fill in the blank, there's some variance because the graph isn't perfect. But if it was multiple choice, then you should be close enough. Yeah, Rachel.
Why does it say 63 underneath products, but then the answer is 163?
So we'll get to what this is. This right here is measuring the difference from here to here.
Oh, okay, that makes sense.
But what we're doing is we're just lining this up
Okay.
with the y-axis.
So it's 160 then?
I said it's 163,
Okay.
but if you said 160 on your paper, I'd be fine with that.
Doesn't it tell you it's just 100 plus 63?
Yeah.
Right, but what I'm saying is that this number most likely won't normally be there. The graph would just be blank. It's there because we're going to learn what it is here in a second. But if it is there, then you should be able to get it more accurately, for sure. Good. And then activated complex in this case, I said it was 226. Once again, if you said you thought it was 225, 222, you're within a range of error because the scale's not super accurate. Questions on simply determining the energy of the potential energy of these three things. Okay, so now let's talk about that number Rachel brought up and that other number on there. So there's two things from a graph that you should be able to calculate. Okay, you need to be able to calculate what is known as the activation energy. The equation to calculate that is we're basically finding the distance from the top of the hill to where we started. One common mistake I see made is often people just look at the top of the hill and they say, oh, that's it. But most of the time we're not starting at 0. So be very careful that you're taking the difference. So in our example, how we got that 126. So activation energy is represented by capital E subscript A. Okay, and we're going to take the top of our hill, which was the 226, and we're going to minus where we started, the reactants, and that's how we get 126 joules. So what that number represents, this is the minimum energy it takes to make the reaction go. If you put in 125 joules, would I see anything happen? We'd stare at an empty beaker or whatever. Nothing would occur. If I gave it, what if I give it 130? Would it go? Yeah, because it's just a minimum, right? You hit the golf ball harder, it still goes over the hill, right? If anything, it actually, that's a one way we'll talk about later that you can make a reaction go faster. So, yeah, Gavin.
So how do you add energy to a reaction? Do you just like heat it up? Or?
Oh, great question. So the energy form we'll mostly talk about in this unit is heat. Yeah. But some other energy forms that like another unit we'll talk about is electricity, is another way in which you can supply energy. And mostly those two I'd say are our main sources. All right, any questions of what activation energy is? Okay, the other thing you need to calculate is this delta H over here, okay? What the delta H represents is this term called enthalpy. It's a fancy word in chemistry that really represents heat, okay? It's not temperature, but it is related to that, okay? The way I remember it is, so it's enthalpy, but the symbol is delta H. Do you guys know what this triangle means? So it's the Greek symbol delta.
Yeah, the delta.
What does it mean, Carolyn?
It's the change.
Yeah, so anytime you see a triangle, it means the change of that. So this is just a symbolic way of saying change in enthalpy. Okay, anytime you see a triangle, the Greek symbol delta, it means change. So what this is we're measuring the overall change in heat of the reaction. So from the reactants to the products, what was the energy or the heat change that occurred? Okay, so the way that we calculate delta H is we take the energy of the products minus the energy of the reactant. So for our example, how we got that 63, so delta H we would take, we said our products was 163. Our reactants we said was just 100, which is how we got 63 joules of energy. So in the end, this reaction absorbed 63 joules of energy in order to proceed. That's why the products are higher than the reactants. Okay? All right, so the next thing that we're going to talk about is classifying reactions in two different ways. So we have what are known as exothermic reactions and endothermic reactions. An exothermic reaction is a reaction that releases or gives off energy. One way people often think about it, or I've heard said, is because it's like exo, so the heat is exiting, and then endo, because it's entering. Right, so kind of a little mnemonic device you can use. Okay, so it's all about the direction of the heat or energy flow. Because the heat is leaving the system, what that means is the products will always be less than the reactants. So when I see an exothermic graph, the products will always be lower than the reactants will be every single time. So what you need to be able to do is we need to be able to learn how to identify an exothermic graph an exothermic reaction, or an exothermic situation. Right? So 3 different things you should be able to classify all as exothermic. Okay? All right, don't say it out loud, but think about it for me. If exothermic means that the products are always less than the reactants, what would that always mean about my enthalpy or my delta H value? What must always be true for exo if the products are less than the reactants? You have an idea, raise your hand, but don't say it out loud. So give you a second to think. If the products are always less than the reactants, what must be true about that calculated delta H? Give me another second to think about it. Amy, what do you think?
I think, doesn't it have to be like negative?
Yeah, very good. It means it must always be negative if it's exothermic. Good. Amy, you can have a smiley face. If you're also raising your hand and thinking the same thing for the people, you can have one as well. So that's another way you can identify an exothermic reaction, is it will be negative. Okay, but we gotta be careful here with this. Can I have negative energy? No. Just like you can't go negative 10 miles per hour. Okay, just because you're driving backwards doesn't make it negative. Okay? So somebody else should try to explain. What does this negative mean?
Energy was released.
Not exactly. It's more so because what does a triangle mean?
It means a change.
Change. So it's really just a directional thing, okay? The negative is not like a negative numerical value, right? When I say negative 80 joules, that means it's lost 80 joules of heat, right? Which in a sense could mean the temperature's changing in certain ways. But be very careful in thinking that it's a negative like numerically, okay? All right, so if the products are always less than the reactants and energy is being released, in an exothermic reaction, it would look something like this, where the energy is after the arrow. So write this in your example box. So exothermic graphs or exothermic reactions always will see the energy on the product side, is another way you could look at it. The energy's on the product side, you know it's exothermic. Okay. In an endothermic reaction, it's the reverse, right? The energy is now being absorbed into the system, or it's being taken in. This means that in an endothermic reaction, the reactants will always be lower than the products because energy is going into them. Okay, so a graph would always look like this. What about my delta H now? What would my delta H always be?
Positive.
Positive. I'd write those down if you didn't before, that exo's negative delta H and endo's positive delta H, just to remind you. Okay, this means that in a balanced equation, we're now going to see energy will be written on the reactant side because it's being put into it. The way I often think about an endothermic reaction, since energy is a reactant, is if I take out energy, this reaction will not go. Because it's a reactant, it's necessary. If you take it out, the reaction won't happen. Endothermic reactions are dependent on that source of energy.
So with exothermic, there was still the little hill thing. So do you need to add energy to get energy?
Yeah, so often what we'll see is exothermic reactions may need a kickstart to get started, like a spark or an ignition. But then once they ignite, they don't need a continually supplied source to keep going. Does that make sense? Like burning gasoline is a perfect example, right? To burn gasoline, it doesn't spontaneously combust, right? If it got hot enough, it could, because then it has enough energy, right? But all I do is if I just put a light to gasoline, it will produce lots and lots of energy, and I don't have to do anything. So, great question. Endothermic, questions on that? Okay, all right, so the next one, what I want to do is treat these next 6 questions as like a mini test for the day. Okay, so pull down your blinders, don't talk to your neighbors, don't look at them. Okay, and answer these 6 questions on your own to kind of see what we understand or if there's things we still have questions with. If you can answer these 6 questions and get them all correct, then you can pass off your I can statement for today. Okay? Obviously, I'll give you, if your answers vary a little bit, because you read the graph differently, that's just fine. It's the understanding that we're looking for. Okay, so the energy for the content of the reactant, you should have gotten around 20 kilojoules.
Oh, is it kilojoules? I didn't
And
know
if you
that.
put kJ, you can have a smiley face. How would I know that it is that?
Because it says
Because
it.
you read the graph.
I can't read that.
Yeah, I don't know what we're doing in chemistry.
Are they capital or lowercase?
It's lowercase k, capital J. And you didn't do it that way, but okay, number 2, you should have gotten around 120. Okay, that's fine. Number 3, around 80 kilojoules. Is this reaction endo or exo? It is an endothermic graph. The value of delta H you should have gotten as 60. Hey, tell me this. Is it ever possible, would you ever write endo and then end up with a negative delta H?
No.
No. So be very cautious. If you're answering both these questions, if this ends up negative, you might want to rethink your answer here, or vice versa. Okay, because this is never a plausible situation, ever. All right, and then finally, your value for your activation energy is around 100. Any questions on those 6? All right, bonus.